Great. Well, I first want to start by thanking the organizers for putting together this conference. I think this is a really great venue. Everything that I'm going to say is joint work with Allison Moore and Claudius Zebrawius. So let me go ahead and start. So I'm going to give a little bit of basic background to set up the story here. So first I'll start with the introduction. So I'll start with the definition. So let's let K be a knot in S3. So here K will just be some embedded circle. And what I'm going to do is I'm going to define Dehn surgery on my knot K. And this is going to be an operation where I remove a tubular neighborhood of my knot. So I remove a solid torus around my knot, and I re-glue that back in some different way to get a new three-manifold. So I define Dehn surgery on K by removing a neighborhood of K, a tubular neighborhood of K, and re-gluing. So it would be good to have some examples to keep in mind. So let's start with the simplest example. We're going to take K to be completely unknotted. So it just looks like this trivial circle. And what do I do, right? So first we're supposed to take a tubular neighborhood of a knot, and we're supposed to remove it from S3, and then we glue the two together. So that's what I've set up here. Now, how does that look like? Well, tubular neighborhood, we just said that's a solid torus. And now if I have a trivially embedded solid torus in S3, the complement is also a solid torus. So what I'm doing is I'm taking two solid tori and I'm gluing them together. Now, let me parameterize this gluing a little bit. So I'm going to draw this curve here. I call this mu, and it turns out to specify a Dehn surgery, I actually just need to tell you where the curve mu goes. So it goes to some primitive curve on the boundary of my knot exterior, my other solid torus. Let me parameterize that boundary. So I'll call this curve L and this curve M. And what I do is I'm going to send mu to P times M plus Q times L, where P and Q are some relatively prime integers. And so what's happening is I'm gluing two solid tori together, and you'll see that what I'm getting is a lens space. That's just the result of gluing two solid tori together. Now here I have to be a little bit careful about what I mean. So when I talk about L1Q, here I'm just getting S3. And when I do L01, I get S2 times S1. So one thing we'll notice is that there are lots of different ways to re-glue back in the solid torus so that I get S3. But more generally, there's infinitely many of these three manifolds that I can produce. I can get infinite pi1, I can get finite pi1, lots of different things. Just to show you that this construction can produce some other more interesting examples, I'll just go to the next least complicated knot, which is the right-handed trefoil knot. And surgery on this produces a lot of different interesting three manifolds. So for instance, surgery produces the three manifold L54. It produces the Poincare homology sphere. So that's a three manifold with finite but not cyclic pi1, so not a lens space. But one can also even get more interesting examples like a torus bundle over S1. So something with infinite and non-abelian fundamental group. So one can produce lots of different three manifolds by this surgery construction. And let me tell you why it's sort of an important notion in three manifold topology. So we have the following theorem due to Licorice and independently Wallace, which says that if we expand this construction a little bit, we can obtain every three manifold by surgery. So I'll say here, every three manifold So here, every three-manifold means closed, connected, and oriented. This is obtained by surgery, now not necessarily on a knot, but on a link. So I take many embedded S1s inside of S3, and I do the surgery operation, and I can produce any three-manifold. So now there's some incentive to study this, and one of the questions we can ask is what we call the botany problem, which asks the following. We want to know which knots surger to a fixed three-manifold. So we've already seen above that there are two different knots that surger to L5-4, so surgery descriptions are not unique. And so we really need to understand this question of how different surgery presentations of a fixed three-manifold can arise if we want to use this in an effective way. So I'm going to start by one of the most well-known theorems in the area, due to Gordon and Lukey, that in some sense gives a unique description of S3. So it says, only the unknot has a non-trivial surgery to S3. So we saw above that the unknot, right, if I send mu to m plus any multiple of L, that'll give me a non-trivial gluing that's reproducing S3. And the unknot is the only knot that has this property. Now, I'll sort of always only talk about non-trivial surgeries, because otherwise we always just get S3 back if we reglue the same way we removed the neighborhood. Now, what is good about this? Let me point out that this has an interesting application to knot theory, which says the following. So this says that if I look at a knot exterior for a knot K1, a knot exterior for a different knot K2, and those exteriors are actually homeomorphic, then my knots were actually not different to begin with than their equivalent knots. So this is the so-called knot complement problem. And I won't say too much about why the theorem implies this, but it's not too hard to verify that the theorem does imply this. So we do get a very deep result about knots once we understand Dehn surgery. And there's a sort of more general interplay between the two areas. Okay. So this seems great. We can detect the unknot, or we have a nice surgery sort of characterization of S3, but this gets really hard after the manifold gets a little bit more complicated. So let me point out the following, which is that it's open as to which knots admit surgeries to lens spaces. And this is what's known as the Berge conjecture, and it's still a very, very long outstanding problem. Okay. So I will say that this is known for some very simple lens spaces like RP3, but in general, we don't have a characterization. There's a conjectural list, but we have no idea how to prove that it's the correct one. Well, there are some ideas, but those ideas haven't panned out yet. And maybe just along these lines, I'll ask the question, which is also open, how to obstruct surgeries, non-trivial surgeries that basically give us a finite fundamental group. So again, these are sort of related to the questions about S3, just in the sense that, well, manifolds with finite fundamental group have positive scalar curvature, just like S3, and they're finitely covered by S3. So this is all sort of a nice, similar family of three manifolds we could all try to lump together. So what I want to tell you about next is a little bit about some ways that we can approach these kinds of problems. So this is not a complete list of techniques, but I want to point out a couple major ones. So the first is what I'll call essential surfaces. And this is very classical. And so I'll just give an example rather than sort of a general theory behind this, but hopefully this will illustrate the idea of how this technique can help us study these Dehn surgery questions. So I'm going to start by drawing a knot. I'm going to draw the square knot. And this knot is, you'll notice that it's a sort of it's a connected sum of two different knots, a right-handed trefoil and a left-handed trefoil. And I want to point out a very interesting torus that lives in the exterior of this knot. So this is called the swallow-follow torus, and it looks like this. So I have this torus that kind of completely engulfs the leftmost knot, and it's going to sort of travel around the rightmost knot. And draw this the best that I can. And you see that what I've sort of built here is, this is not quite right. Let me try to fix this. Sorry. Great, there we go. Sorry about that. So you see this torus now sort of wraps around one side of the knot and sort of engulfs the other. And the key aspect of this knot, of this torus, let's call this torus T, is that not only is it embedded, so T is an embedded torus in the knot exterior, it doesn't hit the knot at all. But we actually can check, it turns out, that this is pi1 injective. So that means that when I look at the inclusion map from T into the knot exterior, it induces an inclusion on pi1. And sort of the key thing to check, this requires some work, but the key fact is that, T stays pi1 injective and embedded in all non-trivial surgeries. And so in particular, that's telling us we're getting Z plus Z subgroups. And so therefore pi1 is infinite. So we've obstructed this knot from having a surgery to S3 or to the lens space or to the Poincare homology sphere. So this is a powerful technique. And it's actually not that special to the square knot. This is true more generally. If K1, if K is a connected sum of two knots, let's say K1 connects sum K2, then all the surgeries, all the non-trivial surgeries have infinite pi1. And the argument works the same. There's this, what we call an incompressible torus that sort of stays, that sort of persists through all the surgeries. So this is a general approach for showing that your surgered manifold is complicated, is by producing a surface in the knot exterior that sort of persists to be essential in the surgered manifold. Okay. So next I want to talk about a little bit more of a modern approach, which we'll call this approach Floer homology. And this takes on many forms, and I'm not actually really going to define, any of them right now, but I'm going to sort of just kind of give a rough idea. So I'm going to say that a rational homology sphere, so a three manifold with B1 equals 0, we'll say that is an L space if the Floer homology, the reduced Heegard-Floer homology, is 0. So I haven't defined for you what this Floer homology group is, but what you should have in mind is that this is something which is geometric or analytically defined. So it comes in a couple different ways. You can think of it as counting solutions to the Seiberg-Witten equations on your 3-manifold, so that's solutions to some geometric PDE. Or you can think of it as coming from counting holomorphic disks inside of a symmetric product of a Riemann surface. It doesn't matter to us how those things are actually defined, but the point is that they come from some sort of analytic data, solving some kinds of PDEs. And that actually can allow us to use some geometric or sort of holomorphic structure to say something about 3-manifolds. So I'll give you an example. So one example is that if your 3-manifold has a metric of positive scalar curvature, then this geometric information obstructs the existence of interesting solutions to these equations. And so one gets that your manifold is an L space. Now, sort of what to keep in mind, metric of positive scalar curvature, that's telling us that, for instance, manifolds with finite fundamental group. So they're finitely covered by the sphere, and so they have these nice metrics. So they have this L space property. So anything we say about L spaces is now going to apply to any of these 3 manifolds with finite fundamental group that we were talking about previously. One other example to keep in mind is that if our 3-manifold bounds a symplectic 4-manifold with B2 plus greater than 0, so all that means is a symplectic 4-manifold with a surface inside of it with positive self-intersection, then actually we get the opposite. We can produce some interesting solution to these equations. We get something which is not an L space. And conjecturally, this is an equivalence if your 3-manifold is prime. But the point is we can now try to use this extra structure, whatever that means, geometry, symplectic topology, and so on, PDEs, to constrain surgery descriptions. So I'll give you an example of the kinds of things that one can say about Dehn surgery using these Floer homology groups. So I'll start with the theorem of Gagini and Ni, which says that if a knot has an L space surgery, again, we always want our surgeries to be non-trivial, so we're in principle producing a different 3-manifold. Then the knot exterior is actually a surface bundle over the circle. So actually, we're getting some interesting information about surfaces in the 3-manifold, in the knot exterior. Now, I want to point out, we said that L spaces include the 3 manifolds of finite fundamental group that we started with, but there's lots of other examples of L spaces. And so now we're getting strong Dehn surgery information about a broader class of manifolds. Some of these even contain incompressible surfaces, for instance. Now, I'll point out that actually there is a little bit of overlap with the results that we just saw coming from essential surface theory. So for instance, we have the following theorem of Krasatovich, which says that if a knot is a connected sum of 2 non-trivial knots, like the square knot that we saw above, then actually no surgery, no non-trivial surgery on K can produce an L space. So using these Floer homology techniques, we can sort of reprove this fact now that surgery on a what we call a composite knot on a connected sum of knots, that will always have infinite fundamental group. But actually we're obstructing these surgeries to a broader class of three manifolds. Now, the question that I'm interested in is sort of seeing this connection is how are these two theories related? So what I want to start with is I want to ask the question, which is what other surfaces can Floer homology see? How can these geometric and analytic techniques tell us about this sort of topological information about surfaces? And so I want to focus on a very specific kind of surface today. So I want to talk about what we call a Conway sphere. So a Conway sphere for a knot is a way of sort of separating a knot into two pieces. So we'll say a Conway sphere for K is a sphere intersecting, this is a sphere intersecting K in 4 points. So I'll just draw an example of this as follows. So I'm going to have my knot, my trefoil knot again. And I'm going to draw a sphere here in blue. And you'll see that it intersects my knot at exactly 4 points. Great. So, and we'll make one extra assumption, or we'll be interested in a special type of Conway sphere. We'll say that S is essential if S minus 4 points. So if we remove these 4 intersection points, this is now a surface inside of the knot exterior, inside of the, say, inside of the complement. Let's say we want this to be pi1 injective again. It's not too hard to actually see that this example is not essential. So I'll leave it as an exercise for the viewer to find a loop which actually gets killed off when we include into the knot exterior. Okay, great. But maybe just a quick thing to observe is that this sphere decomposes our knot into two pieces. We kind of have the part inside of the sphere with the twisty part, and the outside of the sphere, which is sort of this less twisty looking part. And this will be sort of a useful thing for us as we're going to study what happens when we decompose these knots along these Conway spheres. And the theorem that I want to tell you about today is about what this Floer homology knows about these essential Conway spheres. So again, this is joint work with Alison Moore and Claudius Zebrauius. And the theorem is as follows. So it says, if surgery on K is an L space, then K has no essential Conway spheres. And so we could ask, to what extent does this hold in the sort of more classical realm, what was known before in this essential surface theory? And this was actually known, sorry, maybe I'll say it's a corollary. This is a corollary of work of Wu, which says that if some non-trivial surgery on K has finite pi1, then K has no essential Conway sphere. So we've sort of generalized this theorem to the more general setting of L spaces. And so what I'd like to tell you about for the rest of the talk is sort of the ideas that go into this proof and how Conway spheres interact with this Floer homology theory.